Hi, my name is Alexander Scarlatos from the University of Massachusetts Amherst, and I'm here to talk about my work with Professor Andrew Land titled Tree-Based Representation and Generation of Natural and Mathematical Language. Let's start with some motivation. We note that automatically generating math can be quite useful, such as for summarizing mathematical content, generating math questions for students, or providing feedback to students when they might have gotten a wrong answer. We know that all of these tasks require models to have both structural and semantic understanding of math, going beyond what is typically required for natural language generation. So if we want to be good at generating math, we need to be good at representing it. While math is typically represented sequentially, we know that it can also be represented as a tree. In the operator tree format, each symbol in an expression becomes a node in the tree, where operators act on their children, which are either variables, numbers, or other operator subtrees. This representation is useful since the relationships between mathematical objects are explicitly represented. This leads us to our main idea, where we take sequences that contain both natural language and math portions, and we provide them to a generative transformer, but we encode the text and math portions differently. The text portions are encoded in the standard way, but the math portions get special math embeddings, plus special tree position embeddings that tell the model what each symbol's position is in the underlying tree. At the output layer, we ensure that only math tokens are generated in math portions, and that only text tokens are generated in text portions. Finally, we pre-calculate the tree position of new math tokens to ensure that the trees that we generate have a valid structure. I'll first show how we provide tree positions to the model. The position of any node in a tree can be represented as a path that leads to that node from the root. We take each number in this path, get its binary representation, and concatenate these representations to get a unique multi-hot vector. Finally, we transform that vector to the embedding space using a learnable transformation. Next, I'll show how we represent math tokens. Naively, we might want to create a learnable embedding for every token in the math vocabulary. But the issue with this is that some symbols might appear both in text and math, and a separate embedding space doesn't leverage the shared information. As a solution, we come up with a way to share representations between text and math tokens that appear in different contexts. Let's say we want to encode the math token phi. We first look up the text tokens for this symbol, get the associated text embeddings, and take their average. Next, we apply a learnable multi-layer perceptron, which learns an offset from the text embedding. Finally, we add this offset to the text embedding vector to get our final math token embedding. This setup ensures that text and math have the same underlying embeddings, but we add additional parameters with the MLP so the model can represent math-specific information. Now that I've covered most of our main methods, I'll talk about our experimental setup. We initialize our generative transformer with GPT-2 parameters, and then we perform pre-training on all model parameters with a corpus of math-centered Wikipedia articles. Because our model is initialized with GPT-2 parameters, we use GPT-2 as our main baseline. We also compare a version of GPT-2 which is fine-tuned on the same Wikipedia articles to ensure that our gains don't just come from this dataset. The first task we look at is headline generation, where the model is given a question from a Math Stack Exchange post and has to generate the headline for that post. We evaluate this task using text similarity metrics, and while we find that our model, which we refer to as MathGPT, slightly outperforms baselines, the result is not statistically significant. However, we note that using text similarity metrics may not be a fair comparison, since GPT-2 generates math sequentially, but our model generates math as trees. There isn't currently a good metric for evaluating both text and trees together, and we plan on working on this in the future. The second task we look at is equation extraction, where the model is given a math word problem and has to generate the underlying equation required to solve the problem. We evaluate this task by comparing the generated equations trees to the tree of the gold equation, using exact tree match, numerical evaluation of the tree, and tree edit distance. We see that our method significantly outperforms baselines on this task, which shows that our method helps in a setting where only math is being generated, and it may assist with structural understanding of math. Next, we perform qualitative analyses. We compare operator embedding clusters between our model and GPT-2 to see what features our model finds to be important. We notice that while GPT-2 tends to group symbols based on contextual similarity, our model tends to group them based on similarity of their effect, like how GPT-2 groups arithmetic operators together, but our model groups inequalities together. Additionally, our model separates the functionally different min and max operators as well as the intersect and union operators. Now, I'll briefly talk about future work. First, we need a better evaluation metric for comparing sequences that have both text and math that takes math tree similarity into account. Next, since we only experiment with GPT-2, we should experiment with newer and larger base models. We should also experiment with architectures such as encoder-decoder and with larger data sets such as a corpus of scientific papers from arXiv for pre-training the model. Finally, we need to see the impact that our method has on more education-specific tasks, such as generating math word problems and predicting students' open-ended responses to math questions. Thank you very much for listening, and if you're interested in learning more, then you can use the QR code to find our paper on arXiv.